This is Greg Troutwine with Marine Technology TV. We're here at the Oceanology International in San Diego, and we're very pleased to have Margaret Leinen, the director of Scripps Oceanography, join us today. And Margaret, first and foremost, thank you very much for joining us.
It's a real pleasure to be here.
Scripps obviously is an internationally known and regarded center. When you look at the emerging Blue Sea cluster here in Southern California, can you just share what you see Scripps Oceanography's role in that cluster?
Of course. We're very excited about the Blue Tech cluster here in Southern California. This is the first area of this size that has really tried to link the companies that are involved in any aspect of ocean-related industry together with the Navy, together with government. A lot of the things that we have to do depend on that partnership, and the academic sector. So Scripps is really an anchor for the academic sector, and we're very happy to be here.
As we discussed briefly, we could probably sit here and talk for 2 days on all the wonderful things that are happening at Scripps. But you mentioned specifically there are 4 interdisciplinary initiatives at Scripps that you would like to discuss, and starting with climate change impact and adaptation. So starting with that one, can you discuss the 4 interdisciplinary initiatives at Scripps and your role?
Absolutely. First, I want to say that Scripps hasn't given up doing all of its basic Earth, atmosphere, ocean, planetary science, and we'll continue to do that forever. But on top of that, we've taken on 4 initiatives. The first one builds on our excellence in climate research. So we're the ones who started the Keeling curve, which measures the CO2 concentration of the atmosphere. It's the iconic curve of climate change. But now we know climate is changing, so the question is, what's the impact of that? Not just on the ocean, but also on weather, on terrestrial ecosystems, on agriculture, etc. And how can we adapt to that? That in itself is a huge area of basic research, but it also makes the connection into what we all have to be adjusting to in government, in the economy, in national security. So I'll give you an example. We're very interested in the issue of sea level rise. So in Florida, where I used to live, it was ground zero for sea level rise. They have sunny day flooding of the streets in Miami. But here in California, we see that as well. And about a week after I arrived here, the front page of the San Diego Union Tribune was about people who live on cliffs bordering the Pacific, wanting to put concrete over the cliffs to prevent erosion. And that's really because of sea level rise. And it's not just the little incremental rise every year, but it's that compounded with storm surge. So this last year, 2016, was an El Nino year, and we saw erosion of the beaches and erosion of the coastal areas like we'd never seen before. So that means that we're going to have to partner with government to understand how to adapt. I mean, fortunately, we've probably got about 30 years to develop and implement this adaptation, and there are going to be a lot of business opportunities there. How do you best do that? What systems are most vulnerable, and so forth. And we think we can help answer those questions.
Spectacular. And when you look at the second initiative, I believe you couched it as resilience to hazards. Now, what do you specifically mean by that?
Well, almost any kind of natural hazard that Scripps studies, earthquakes, tsunamis, flood, drought, all of them. And our goal, since it's very difficult to predict long time ahead of an event that we're going to have one of those, how do we improve our resilience? So a great example is earthquake. the very southernmost segment of the Great California faults is the San Jacinto Fault.
Okay.
It's just east of here. When that fault goes off, and it's almost 300 years overdue,
Okay.
we will have about 30 seconds of notice in San Diego because we have that fault instrumented. So, because light moves faster than seismic waves, we can send signals back to San Diego that can be linked up with systems that would do things like raise the doors, the garage doors for police, fire, so they're not trapped in a building. It could set off alarms in schools so that kids can get to safe places away from windows in structurally secure areas. It could turn on the emergency generators at hospitals so that they're not left with patients on respirators who aren't working, and alert people to interrupt surgeries, do everything that we need to do. So we can't predict the earthquake, but we can improve our resilience to it a lot.
It must be nice to do something that has such a broad impact for humanity. That's absolutely amazing. Your third initiative is human health and the oceans?
Yes. So if you Google human health in the oceans, you see seafood safety. Does my tuna contain mercury? Or PCBs or something like that, and harmful algal blooms. So we're definitely working in both of those areas. For example, we're developing technology that would allow us to very rapidly determine the PCB content of a fish. Now, right now, we have to kill the fish, take the flesh, prepare it and analyze it. But you'd like to be able to just, at the seafood hacking plant, rapidly determine whether there's any problem. So that's a technology that we're developing. Harmful algal blooms, we're focused on being able to predict those well in advance so that water intakes can be shut down, beaches can be posted, and so forth. But there's far more to it than that. Those are all sort of avoiding harm. There's also helping out. So over evolutionary timescales, organisms in the ocean have developed very elaborate defenses, usually molecules that protect them against predators, corals that protect themselves against being nibbled by other creatures. So those molecules are targets for us for new drugs. And what we've been developing is new drugs from marine natural products. A great example is a new drug that's coming from an algae that was found right here on the California coast. And it is proving to be very effective against MRSA.
Oh, wow.
Yes.
Excellent.
Oh, wow.
Wow, that's amazing.
If this goes through its trials and is approved as a drug, it would be the first new antibiotic in 25 years.
That's amazing.
So there are a lot of aspects of human health. There's also things like the sea spray from the ocean concentrates bacteria and viruses and organic molecules. So is that giving us over long periods of time great resilience to things that are in the ocean? You know, that small dose that leaves you immune? Or is it a chronic irritant? It's another issue we're trying to resolve. So there are a lot of complex issues regarding our human health that are firmly rooted in the oceans.
Margaret, you had a fourth initiative, the innovative technology to observe the planet. As I said, a nice tiny little topic, but when you look at that fourth initiative, what does it mean to you?
Well, we're developing sensors. For example, we've partnered with others to develop a sensor for pH to be able to measure the acidity of the ocean very rapidly. So 5-6 years ago, in order to measure pH, you had to go out, take a water sample, do wet chemistry on it. It was a very long, involved measurement. Now we have sensors that allow us to do that are very stable over time. We can put them on a mooring in the ocean, or put them on instruments that we can tow through the ocean, or instruments that we can leave on a coral reef. So we can start to understand how this issue of ocean acidification will play out, where we're most vulnerable, what we could do about it, and so forth. Another example is what we call platforms. So one's a sensor and measures something, another is a platform that you put a sensor on. So this morning I talked about miniature autonomous exploration units.
Okay.
And that's a code for a device that might be about as big as a cantaloupe, that would have that would be autonomous, would float in the ocean, and not only would go by itself, but could swarm with other floats to go out and measure a large area. And they can communicate with each other. They can keep their position together. They can hold at a constant depth. So they could measure things like temperature and salinity and so forth. Eventually, we think they'll carry cameras and other kinds of sensors. So that's a platform. And then there are systems. And what's a system? So right now, we have a microwave communication system that is all over Southern California. It sends microwaves from instruments like seismometers up to the top of mountains, and then mountaintop to mountaintop back to Scripps. So we can monitor in real time seismometers that are out on the San Jacinto Fault. And this has such high bandwidth because it's microwave that we can also put cameras on tops of the mountains, and they're being used by CAL FIRE, our firefighting utility, to detect wildfires very early on, to see the direction that they're moving, and to deploy their resources safely. The other thing that it's doing is one of those mountains is Palomar, and all the data from the Mount Palomar Observatory is going through our microwave communication system back to Mount Soledad here in San Diego, down to Scripps, and from there out to the world. So that's a system for observing the planet and also the stars and galaxies.
When I look at Scripps, my head literally spins with literally with all of the work that you're doing. If you had to consolidate in a sentence, in a paragraph, what you consider to be the strength of Scripps Oceanography, what would that be?
Understanding and protecting the planet.
Again, a very noble cause. And again, I very much appreciate your time. Thank you.
My pleasure.
This is Greg Troutwine with Marine Technology TV.